Okay, so we are live.
Okay.
Wait a couple more minutes before we start.
Hey, Peter. Hi, Andrew.
Right, so we are streaming and we will shortly start also cloud recording. Okay. Yes. Okay, so hi everyone, and we have now the third and final talk in Pierre's mini course, and we will later have also the final talk by Asaf Nachmias today. And as you know, we have other courses. We have a single course next week. So next week we have Nathanael Berestiki who will speak about multiplicative chaos, Gaussian free fills, Brownian loop soups. But please, Pierre, you can continue.
Okay, thank you very much for the invitation and for the introduction. So I'm giving the last lecture on star edge reinforced random walk, Bayesian statistics and statistical physics. So before, I know we already did a lot of computations, so I think we deserve a little bit of fun. So I have some simulations I want to show. Actually, they are not from me, they are from Andrew Swan. So let me show the first, which is, okay, I have a problem that, yeah, on the edge reinforcement framework. So you see, actually, it already from the beginning it gets quite stuck. So which you may not expect as radically. At least I didn't. Let me also show a faster one.
This was linear reinforcement?
Yeah, linear reinforcement. Now I'll show a faster one with which shows more kind of the limiting measure which appears. Okay, so I hope you enjoyed. Okay, so now we start again. So so in the last two lectures, we started by the case of polyiron, and so we explained how kind of confronting the quench and the annealed version, there was a way to find the limiting measure. Then we applied the same technique for the edge reinforced random walk. Then we explained why we can write the edge reinforced random walk, so which is reinforced by the number of edge visits to crossings of non-oriented edges. So and so we showed that this edge reinforced random walk can be written as a mixture of vertex reinforced jump process. So the vertex reinforced jump processes are processes which are reinforced linearly in the local time. So basically you jump from I to j at a rate which is wij multiplied by the local time at j plus 1. Okay, so but by convention you start with that local time equal to 1. So you write just wij lj. So we showed that the edge reinforced random walk is a mixture of so the edge reinforced random walk with starting weights AE, so at non-oriented jet E, is a mixture of vertex reinforced jump processes with parameters, conductances WE, which are distributed as independent gamma random variables with parameter AE. And so so we explain why that vertex reinforced jump process. So let me show the beginning, so the outline, so that you can see more. So so then we showed, yeah, first so that okay, there were 3 time scales in which you could consider the vertex reinforced jump process. So one is the exponential time scale, in which locally in time it's a reversible process. There is another one in which is exchangeable, in the sense of partially exchangeable, the process in the sense of Diaconis and Coppersmith, and a third time scale, which is actually the original one, which is a linearly reinforced one. And so we saw that as a consequence of partial exchangeability of the VRJP, we can again write it as a mixture of Markov chains. So what we are going to do today, so first we are discuss the Bayesian approach to find the limit measure. So you see that it's actually, in some sense, it's simpler, but it's a little bit twisted. So it's really interesting. Then we discuss another approach for describing that limit measure, which goes through a random Schrodinger operator, which is independent at distance greater than or equal to 2. Then we'll discuss applications to recurrence and transience, and then the star edge reinforced random walk, and its properties. So let's go back where we were. So let's see. Yeah, so the last thing we did last lecture is, so we computed this measure, okay, this is next slide. So we computed the probability of a given path, and we had this nice formula. So this formula will be important in the computation we are going to do now. So now let me explain the Bayesian approach. So we start. So we call mu I0W the law of the limit random variables U, under which the VRJP is a mixture of Markov processes with jump rates which are 1/2 of Wij e to the uj minus ui. So we have computed the annealed probability of a path for the vertex reinforced jump process. So it's this one, right? So, but we can also compute the quench probability of a path. So it's an easy computation. So it just relies on the fact that because your jump rate from I to j is 1/2 of Wij e to the uj minus ui. So your jump rate out of I is the sum of that for quantity for j adjacent to I. And you have this so term e to the uj0 minus ui0 which corresponds to the telescopic product you have when you do the jump, the jump probabilities, and this product of jump probabilities, which is the same one you have at the end of the formula for the annealed one. So now we'll introduce some notation. So we'll put some bracket when, so we renormalize the U's in such a way that the sum of the UIs become equal to 0. So we subtract 1 over the number of vertices multiplied by the sum of uj. And so now the first remark we make is that after we condition that vertex reinforced jump process on a path up to time t, we have new weights. So this is a new potential. So wij square root of 1 plus si square root of 1 plus sj, and u prime, which is u minus that normalized, so 1 over 2 log of 1 plus s. So this is simply a consequence of that lemma here that we did last lecture. So here, just note that because u up to a constant, an additive constant, is 1/2 of the log of L, you get indeed that 1/2 of log of 1 plus s that you subtract when you go from u to u prime. And then you just make sure that the sum is equal to 0, of the u primes is equal to 0, so which is why you can take the bracket. So the condition, yes?
I have a question. Why is it that when you do this conditioning, you need to do a rescaling of everything?
So this is
to get it back into the exchangeable timescale?
No. So this is this lemma that I did last time. So the proof is here. So you basically you simply rewrite. You take a new weight, new local time when you condition, and you can rewrite the process like that. So as a VRJP, starting with those new weights after that local time change. Okay.
Why do you do you don't need to do the time change.
Sorry.
So the time, you can always do a time change if you want, but there's some reason, I guess, you've decided to do this particular time change.
Yeah, because this is the time change under which, with the definition of VRJP that I took, I get a new VRJP. Otherwise, I wouldn't get a new VRJP. Okay. So, does that answer your question, Andrew?
I think I probably just have to calculate it, but yes.
Yeah, so yeah, just look at this slide. So anyway, so the point here, what I'm just going to use now is that after that time change, I get this VRJP with those new weights, right? And then the u prime would be the u minus the log 1/2 of the log of 1 plus s. So and which is proof here. So whether this is the only one you can do, again, so this is the only one because because of the definition of the RJP we took, where we start with a local time which is 1. So otherwise you would have other ones. So but let me continue. So so now you compute the probability starting from I naught with so conductances W of your limit random variables U being between U and U plus DU, condition on your path. So the path that I described, that you start at I0, you spend time between V0 and V0 plus dV0 at I0, you jump to I1 and so on, and then you jump to IN until you reach total time T. So same computation as before, you simply get the phi I0W of U multiplied by du, you multiply by the quench probability, you divide by the annealed one. So, and then you say that this corresponds to the phi of the new VRJP. So with with those weights, so WS. So let me remind you that here Wijs is Wij square root of 1 plus Si square root of 1 plus Sj, and with the U, which is changed into U minus log of 1 plus S over 2. And then taking off the average in order to have the sum of those U primes here being 0. So, so you get that formula, which is here, so that phi J0 Ws of that U minus log of 1 plus S over 2 is equal to that quantity. And then, so, I mean, it actually looks a little bit more complicated than the formula for edge reinforcement homework, but it's easier to use. So the way you do it is first, so you apply the formula for for two choices of S. So the first choice of S you use is the one in which you take 1 plus Si equal to e to the 2 ui. Okay, so you can multiply by a certain h. So actually, you should actually multiply by a certain h here. So I didn't, but so it wouldn't change the result dramatically. So then you would get, yeah, because so here you have to be careful the way I write it here. You could have, let me see. Yeah, you want the S to be positive, so you have to multiply by a certain h. So that was actually the earlier version of the slides, but I didn't realize when I changed. So, but you can do that. So if you multiply by h, it doesn't change. So actually the computation we do, the next computation we do after that one. So you take. So when you apply for that, so here you would get 0, because so if you take 1/2, so at the quantity here, the U prime here, U minus log 1 plus S over 2 becomes 0 because of the fact that 1 plus S is e to the 2U. So multiply by a constant. So you get that. Then multiply by, so that phi J0 Ws of 0, which is phi I0 W of U, multiplied by exponential of 1/2 of sum of, for I, J, such that J is adjacent to I, of Wij, e to the Uj minus Ui minus 1, multiplied by e to the minus U0, Ui0. So here you simply do the computation. So when you have 1 plus Si equal to e to the 2 ui, so the product here on the right hand side, it becomes the product of the e to the u e to the ui for I different from J0, but then you have the e to the uj0 here. Now you have assumed that the sum of UJs is 0, so that term it simply gives you a factor 1. So you get the e to the ui0, so e to the minus ui0 here on the denominator. So now the SI is is e to the 2ui minus 1. So the e to the 2ui gives you a sum of Wij e to the ui plus uj. But that quantity you get also on the right hand side, on the denominator, because of the square root of 1 plus Si, square root of 1 plus Sj. So the only term you have to consider is the minus 1 here. So that gives you the sum of 1/2 Wij e to the uj minus ui, and then also the minus 1 part of the part in the exponential in the denominator. So we had that formula. On the other hand, so you you consider the operation of multiplying all the weights by a certain constant h. So if you do that, so obviously the term here, bracket of log of, so that is basically S equal to h minus 1, Si equal to h minus 1 constant. So then the bracket of log of 1 plus s over 2 is 0 by definition. So you get phi gi0 ws of u equal to phi i0 w of u, and multiplied by, so here the term on the right hand side, which is the product of the square roots, it will give you an h to the power of, so number of vertices minus 1 over 2. So, and here so if you replace the SI by h minus 1, so 1 plus SI then is simply h for all i's. So for instance, the product of the square roots is simply h, and the SI, so as SI. So sorry, SI is h minus 1, and so therefore you get actually that phi I0 WH of u is phi I0 W of u multiplied by that quotient. So multiply by h to the v minus 1 over 2. And then you do the same technique, which is to note that, so this quotient here of eta WH of u over eta WH of 0, which is here where eta is, so where eta WH of u is defined here. So the exponential of minus 1/2 of sum of Wij e to the uj minus ui h minus 1. So you see that if h is very large, that quantity, so h very large, will make this measure extremely small unless ui and uj are close to 0. All the ui's are close to 0. If they are close to 0, you can go do Gaussian approximation. So it's exactly the same spirit as in the last two lectures. So the Gaussian approximation here is simpler because it actually only gives you the Gaussian free field. And it's normal that it's simpler because when you go from edge reinforced random walk to vertex reinforced jump process, you take off the gamma of AE independent random variable. So it's normal that after, so you get somehow a cleaner process. So now this concentration of the measure here, phi I0 WH of u around 0 when h is large, enables you, together with the fact that so the integral of phi I0 WH is 1, so it enables you to find the constant phi I0 W of 0. So here you define so dW of u, so it's a quantity similar to the ones we looked at before. So it's again, it's a principal minor of the Markov chain, the generator of the Markov chain with jump rate Wij e to the ua plus uj of diagonal, and such that the sum over all lines is 0 of your matrix. So then you get minus sum over the diagonal. And so this, by the matrix tree theorem, again, you can write it as a sum over spanning trees of the product over edges in the spanning trees of Wij e to the ua plus uj. So, but by that, so Gaussian renormalization, so you get that phi I0 W of 0 will be number of vertices n divided by square root of 2 pi to the n minus 1 over 2 multiplied by that square root of that principal minor. And then you come back to this formula 3.2 here on the top. So you can compute the left-hand side, so that's what we did, and the right-hand side. So then you just take off the exponential and the e to the ui0 from the right-hand side. That gives you the limiting measure. So, so again, it's a little bit involved, but I find it simpler. At least the Gaussian integral is much less painful than in the edge reinforced random walk case. So, so that's for. So that limiting measure. So in summary, you obtain that guess that so the limiting measure u should have density n over square root of 2 pi to the power of n minus 1, multiplied by that term e to the ui0, which emphasizes the dependence on the initial site, I0, multiplied by e to the minus h of wu. So here I wrote two sum of wij hyperbolic sine squared of ui minus uj over 2, but you could write it, so you could replace the 2 sin squared by cosh minus 1. And so I've rewritten here the principal minor. So are there any questions here? Okay, good. So this is the limiting measure. So again, so now if you want to prove that it is indeed the limiting measure, you have various approaches. So one is to recognize that integral as a known integral, and it is actually a known integral. So it is the marginal of a Gibbs measure on the supermanifold extension of the hyperbolic plane with that quadratic action, but taken in horospherical coordinates after integration over fermionic variables. So the next question is, okay, so you have this H22 model, so where does it come from? So with Merkel and Rollers, we tried an approach which is basically doing the same as Keen and Rollers. So we know the probability of a path, and then we sum up over all paths with given local time. And indeed, we find an extension of the supersymmetric model. In particular, so the interesting part is that the last exit trees of, so we again find an interpretation of the last exit trees of the walk, as in the paper of Keen and Rollers. So this is not surprising, still interesting. So, and we know that that those last exit trees are actually a tree version of harmonic variables. So there is a completely different approach. So very nice by Roland, Barbara Schmidt, Tyler Helmuth, and Andrew Swan, where they find actually Linkin's isomorphism. So I mean, okay, Linkin's isomorphism actually was discovered by many people. So Bridges, Froelich, and Spencer first, I think, or there was also some early work by Szymanczyk, by Lüttinger. So they find that what is Linkin's isomorphism? It's an integral identity which relates the local time of a process. So let's start with the Markov process. So for instance, it would relate the local time of that Markov process to the Gaussian free field. So basically it would so more or less show that that local time would be okay, of a loop soup would be 1/2 of the square of the Gaussian free field. And so what they show is that so this is for Euclidean geometry, but if you change the geometry, so if you go into the H22 geometry, then you find a new BFS Linkin isomorphism, and that isomorphism is for the vertex reinforced process. Okay, so let me now explain the link with random Schrodinger. Operator. So we define those beta i's. So let's start with the first part. So 1/2 of sum for j adjacent to I of wij e to the uj minus ui. So this we already know what it is. So this is the jump rate starting from I. And then we add a term here, which is a gamma random variable independent of the field U, only at the starting site I naught. And so this field, which we will call beta I here, will have many interesting properties. So one is that it's one dependent. So the beta on V1 and V2 are independent if the distance between V1 and V2 is greater than or equal to 2. Another one is that, for instance, so on ZD, for instance, with constant W, it is translation invariant. So, and the third one is that so the marginals are reciprocal inverse Gaussians up to constant. So here I'm talking of joint work with Szabo and Zhang, Xiaolin Zhang. So and then so you can compute the distribution of the betas. So if you listen very carefully, you would notice that actually the computation of the probability of a path that we did gives you an expression for the Laplace transform of the betas. So because you know, so that probability involves the Laplace transform here. But here we are going to write the distribution instead. So we let again the Wi be the sum for j adjacent to I of the Wij. We let delta be the discrete Laplacian, so the matrix with the off-diagonal coefficient Wij and diagonal coefficient minus Wi. We define now the random Schrodinger operator, so which is minus delta plus 2 beta, and I don't think there should be a minus W because we already took it. So H beta here. So we assume, basically our the space on which we will integrate is the one on which H beta is positive. So we can actually show that the betas we took here, so which are the 1/2 of the sum of e to the j minus ui wij plus the Dirac, are actually give you a positive definite beta. So therefore, so we see then, so H beta is an M matrix. So H beta inverse has positive entries. And then, so you can write this, so the distribution of the betas, so which looks like a Wishart distribution. So actually it is, it can be seen somehow as a Wishart distribution condition on off diagonal coefficient being minus being Wij. So okay, so that's it. So now so how do you retrieve the u out of the beta? You simply take the green function. So it's a simple computation. Here you have, for I different from I naught, you have that beta I is 1/2 multiplied by the sum of Wij e to the uj minus ui. So this gives you that H beta taken at e to the u is equal to 0. And again, I think there shouldn't be a minus W because we already took it off. So so this gives you, therefore, that e to the u I should be g of I0 I over g of I0 I0. So therefore you have, so to summarize, so what does this random Schrodinger approach give you? So it gives you that a potential beta. So this is the potential of your random Schrodinger operator minus delta, so Laplacian plus 2 beta. And so this potential does not depend, so it will have this distribution here on the bottom. What is important is that it does not depend on the starting point. So what will depend, so the dependence on the starting point only appears when you compute, so e to the ui. So here I wrote e to the ui as g of ui0i over g of i0i0. So it's normalized such that ui0 is 0. So this is not here such that the sum of the ui's is 0. So you could have a more complicated formula doing that. So you have these betas which are independent, so which do not depend on the starting point. They are independent on distance greater than or equal to 2. And so out of these betas, through the green function, you get the u. So which gives you this Markov jump process with jump rate, so which enables you to reconstruct the jump rates. So okay, so let me now say quickly the implications in terms of recurrence. So actually, so that part is really owes a lot to the two papers of dissertory Spencer and Schoenbauer. So one about delocalization. Of that field, so that field here, that supersymmetric field on H22, so the other one on the localization. So the result they get is that, so if the W's are small, so which corresponds to strong reinforcement, then the field is localized, and if W is large, which corresponds to weak reinforcement, then the field is delocalized. So we could translate those results into saying, so with Christophe, into saying that the edge reinforcement on the work and the VRJP are positive recurrent as strong reinforcement. So this is the localization result, and the delocalization result. So we had to work a bit more. So we wrote a paper with Margarita Dissertori, showing that indeed. So okay, for the VRJP, it was the delocalization. So the transient phase, was a consequence simply of the paper of Dissertori, Spencer, and Schoenbauer. But for the edge reinforcement work, we had to look at another field, which is average over the WEs with independent with gamma distribution. And for that, we needed to make some changes in the proof. So, but in both cases, we could show transience. So the fact that eventually, so the starting site is not visited anymore. And so now Sabo and Zhang, so using that random Schrodinger approach, showed that the edge reinforced random walk with constant weight is recurrent, for any weight A in dimension 2, and Pudvin showed that if you have monotonicities, so namely that increasing initial weights of the edge reinforced random walk on the VRJP makes the walk more transient. So you have a unique phase transition. So now that I've stated all these consequences, let me mention that there is a paper of Angel, Crawford, and Kozma, so published in 2014, which shows recurrence under more or less the same assumption of the same theorem, the first theorem I stated, so which is that you have strong reinforcement, but without using that limiting measure. So I intended to give you the proof, but I really won't have time. So the idea somehow is that, so if you so you make use of the fact, so you look again at the tree of first visits, and on this tree of first visits, you have that, so if you visited J first from I, so you know that you would have waited so an exponential time. So if you look in the linear time scale of the vertex reinforced jump process, so you would have waited an exponential time at I before you reach J, because so you want to J through I. So more, I mean, if you want to make that rigorous, you have to introduce a coupling between the two. But so, and then, so now if you look at the time you spent at J before you first come back at I, you know that when you arrive at J, because you will have waited that exponential time, your time would be 1 plus that exponential random variable. So it would be an exponential, the time you have to wait would be an exponential with that 1 plus exponential random variable. Now, you can, on the other hand, so you use two hats. So on the other hand, you use the fact that the walk is exchangeable. So the VRJP is exchangeable. So it's a mixture of Markov rank process. So somehow the time you have to wait at I before you reach J divided by the time you have to wait at J before you first visit I. So that time it gives you a good estimate of the e to the ui uj minus ui. And so by using that technique, so you have inequalities that states which estimate you get, and using that technique, so you can get that exponentially decreasing decrease of the UI with the distance on a finite graph. But then you can so that's enough for you to prove the recurrence on that finite graph. Okay, so I won't have also time to mention so some work we did with Titus Lupus, so in particular on the introduction of a new process, so which is a continuous in space version of the VRJP, and also of the what we call the reverse VRJP. So I now I have only basically a little bit more than 15 minutes to talk about the star edge reinforced on the MOOC. So let me jump to it. So okay, so let me first give that statistical so that motivation from statistics. So let's start with K-dependent Markov chain. So K-dependent Markov chain is a process which instead of having probability starting from a site depending only on your state or that site, it depends on the K past locations you were at. So you process Y, it will depend on Yn minus K plus 1 up to Yn. And then, so another way to say it is simply that your process is actually Markov, but when you look at it with the memory of the K past places you were at. So let's call IA up to IK, so the last those last places, and so what you do now, so when you jump from IK to IK plus 1, is you consider the word which ends up with IK plus 1, so you add one element to your word, and you remove one because you don't need I1 anymore to have your Markov process. So that gives you a transition rate on that divergent graph. And then, so you can define an extended version of reversibility, which is that under the invariant measure for that process, the law of the process is equal to the law of the reverse process. So when you go from y1 to yn. So the vector y1, yn is equal in law to yn up to y1. So if you started from invariant measure. And so you can write it also as a modified balance condition. So here note that the omega star will be the flipped string. So so basically it's the word that you take but backwards. And so note that so what we are going to do now is define a process with the star map, so which is in involution. So when you do the fixed string is obviously an evolution, but we will only assume an involution. So we won't assume anymore that word structure. So on the Debrecen graph. So okay, this is the framework. So you have now a directed graph, not undirected, but I'll keep the same notation VE. With so that involution star, such that so if an edge ij is so if ij is an edge, then j star I star is also an edge. So let's define. So we'll use it several times for the star edge reinforcement homework and VRJP also. Two sets. So one is the set of self-dual points, so the I such that I is equal to I star, and another one is simply an arbitrary choice, so V1 such that you can write V as a disjoint union of V0, V1, and V1 star. And let's take some initial weights. So here you need the condition that alpha ij equal to alpha j star I star. So now you define that process. So it starts again at the fixed site I naught, and so the conditional probability given the path is equal to is proportional. So to go from I to j is proportional to numbers of crossings from I to j plus numbers of crossings from j star to I star, with the convention that initially you have that number of crossings, that sum being alpha ij. So the whole thing divided by, so when you want to write the probability, you have to divide by the sum of all those steps. So note here that when you take star being the identity, you simply find the edge reinforcement homework. And so we already discussed that the case where you are on the set of words and star is inverting your word. So so now let's define the divergence of field Z. So this will be the sum of outgoing Zij minus the sum of ingoing Zji. And let's define that spooky constant here. So gamma of I0 alpha. So this is, if you look at the first part of the numerator and the denominator, it's basically the one we had before for the edge reinforcement homework. And then we add, so this is for the I on the numerator, it's for the I in V naught. And then we add, multiply by a term for the I in V1 of gamma of the minimum of alpha I and alpha I star. So the E tilde here is is an equivalence class. So somehow I think I've written, no, I haven't written it. So basically, E tilde corresponds to the fact that you just take one element out of ij and j star I star, so you don't take it twice. So because otherwise you would have twice a gamma of alpha ij. So and then so you can so here you have partial exchangeability, but for that exchangeability you need some initial assumption. So it's a good computation to make. So it's based on the following fact. So when you start from a self-dual point, so you know that, okay, so when you leave, you have to add one to one of the outgoing edges. When you come back, you will have also to add one to the one of the ingoing one. So you have exactly same type of structure that you had two in total to your alpha I. But now when your site is not self-dual, so when you leave, so if you come back to the same site, you'll have same structure. But if you don't come back, what happens? So let's say you go from I naught to I naught star. So when you go out, so your alpha, so ij will increase by a term which is your alpha I0 will increase by 1. Your alpha I0 star won't increase. And then when you arrive at alpha I0 star, your alpha I0 will again increase without the alpha I0 star increasing. So but now if you assume, so what happens is that you're in the whole operation where you go from I0 to I0 star, your alpha I0 will have increased by 2, whereas your alpha I0 star won't have changed. And that's why you need to have that divergence equal to of alpha equal to so that Dirac at at I0 star minus Dirac at I0, so you have a so basically when you arrive, so you had this alpha I0 which would have been on the denominator, so which was on the denominator when you computed the probability. Now when you compute the probability arriving at I0 star, you want alpha I0 plus 1. And you know that your alpha I0 star won't have changed in the meantime. So that's why you need that condition. So you need a little bit of thinking to understand that. So here, so you'll excuse the typo. So I computed the nil probability, but the formula here is wrong because you should have also the one which is involved in the with the V1 side. So the only part of the formula which is right is the one which goes from the top left to the top right. Sorry, so from the left to the right. So that probability is indeed, again, you can indeed write it as gamma I0 alpha over gamma J0 beta. So it has this simple structure. So it's a good exercise to do. So why was it introduced, that process? So it was introduced for the statistical analysis of molecular dynamics simulation with reversible laws. So by Bacaliado. So Bacaliado was a student in Stanford in chemistry, and actually he met with. So he was looking at that question of statistical analysis, and he met with Percy Diaconis, who proposed that generalization, and so who made him work on that. And let me mention two applications. So beyond that Bayesian analysis of higher order Markov chain. So the first is variable order Markov chain. So instead of having a Markov chain of fixed order, you jump from so somehow from one side to the other. If your words ends, so you just look at the context of your word, as they say. So which is the transition probabilities out of X and Y are the same if X and Y have the same context, which means that they both end with the same subword. And you have also another generalization a random walk with amnesia, so which starts to concern me. So one is when you can forget, so basically a part of the word, so the first element of your word, or you can append one. And so it can be seen as a generalization of the above. If you disallow appending when the words end with the same subwords in the context set. So, okay, so now, so what are the limiting measures? So we saw that, so the divergence of x has to be equal to 0. So why? So here we started with divergence of alpha equal to delta I0 star minus delta I0. It's an easy exercise to show that as time goes on, when the alpha evolves, so let's say at time n it is beta, so as in this formula here. So when it evolves, so then the divergence of beta at time n will be delta of xn star minus delta of xn. Then it's easy to see that if you renormalize the field by the time, you will converge to something, an object which has divergence 0. Yeah, I already defined E tilde, which is the set of edges quotiented by the ij equivalent to j star I star. And then, so you have to, so this divergence free condition gives you that you need to choose a basis of the x's. So it's a bit more complicated than for edge reinforced on the MOOC. So you choose a basis B, and then you look at the Lebesgue measure product of dxe over B, and you obtain so that limiting measure. So again, if you are brave enough, so you will notice that the gamma I0 alpha, so it has no surprise to you. So if you actually listen carefully, it's no surprise that it appears here because it corresponds. You know that the quotient of those gamma I0 alpha will correspond to the annealed probability. On the other hand, you know that this term here, product of ij over ij in E tilde of xij to the alpha ij minus 1 over that product of xi to the alpha I over 2 corresponds to divided also that by the product of square root of xi. No, not by that. So you don't need. So this corresponds actually to the quench probability. So therefore, you know that. Yeah, and you would have a square root of So yeah, you may have a square root of x at the end site minus divided by square root of x at the initial site term. But anyway, so you with the same technique as before, you understand why your function here, your limiting measure should have. So that renormalization gamma of I0 alpha, and should have that term basically multiplied by a certain quantity which does not depend on alpha. So which here is square root of xi0 divided by the product of over I in v0 of square root of xi multiplied by square root of d of x. And how do you obtain that? Again, by same technique, you let alpha go to, so you let the time n go to infinity, alpha go to a certain beta, and your integral will localize. So it will be concentrated around beta with Gaussian Gaussian randomness, and so that will make this square root of d of x appear. Okay, so now the star vertex reinforced jump process. So is defined as the vertex reinforced jump process, but it jumps from a site to another at a rate which is so from I to j at a rate which is wij lj star. So, and again by same technique that we had in So in my paper in 2011 and the paper with Christophe in 2015, you get that so the star edge reinforcement above can be seen as a mixture of star vertex reinforced jump process. Okay, so and so so now what I wanted to discuss quickly is so first, so what this star vertex reinforced jump process is. So first remark, it's not an exchangeable process. So it can be, it's actually not so surprising if you note that you needed a condition here on the alpha such that you would have exchangeability. So you somehow you needed to how to say, to average your starting measure in a nice way in order to find that exchangeability. So if you don't do that averaging, that doesn't work. So this is not partially exchangeable. So it's not a mixture of Markov jump processes, the star VRJP, but so you can still do something. So okay. So let's first note quickly that the limiting. So actually, you will still have a limit for the Ti minus of T of minus T over V, as actually you get. So here, so I'm writing it here in the exponential time scale. So here I said that the jump rate was Wij Lj star, but if you again write it in another time scale, you get Wij e to the Ti plus Tj star. And so in that time scale, you obtain that, so that limit exists and that it belongs to that manifold L0W with zero divergence. Okay, and it's a simple proof, which basically relies on the fact that the Z, the limit Z, so renormalized, will have zero divergence. So I don't have time to explain it. And then, so what we do is we say, okay, it's not an exchangeable process, but if we now average it over some initial weights, it becomes exchangeable. So we take that averaging measure, nu I0W. So here f of Wi0 is simply the renormalizing constant. And so we can show so that so if you actually start the WE start with gamma of alpha E, then it includes actually that averaging in the sense that when you take the WA, so here WA I didn't write, it's simply W to the, so WA at ij, it would be W to the AI plus AJ star. So the WA in low will be equal to W. So when you do that averaging over the gamma random variables you had when you went from gamma star edge reinforcement number to star VRJP, that doesn't change anything in low. And then, so this process after that averaging and after putting in common the local time at I and at I star, it becomes again partially exchangeable, and it's a mixture of Markov processes, Markov jump processes with jump rate e to the uj star minus ui star over 2. Okay, and so the limiting measure is this one, and you can take the same remark if you can guess the f of Wi0, and you can guess you can get the FWI0 from the annealed probability, and the e to the minus sum of Wij e to the uj star minus ui star from the quench probability. And then again, so the term you have here corresponds to the renormalization when you make that measure concentrate. Okay, so let me finish by that. So I wanted to talk also about some nice identities, but I think I've already gone past my time. Okay, so thank you very much for your interest.
Thank you, Pierre. So I suggest we all unmute and thank Pierre for the mini course. And okay, and we can take questions. I will also stop the recording.
So why? Sorry. So
Yeah.
why is the orientation important? Like, is it would it also work on an unoriented graph? Or?
So what do you mean the orientation?
That somehow that you define the star edge reinforced walk on an oriented graph, and there are weights on oriented edges, and
Yeah, this is different. So let me. So I haven't mentioned, but for instance, we have a paper of Sabo, which is I think 2009 or something like that, on the oriented. So if you do the oriented edge reinforced random walk, so simply you take, let's say you take ZD, and you reinforce only by the number of visits from I to J, right? Not, you don't include from J to I. So then it's simply, you have a polyhedron. In that case, you have a polyhedron at each vertex, right? Independent polyhedron at each vertex. And you do that on Z3 or ZD, D greater than or equal to 3. So actually, it is transient for any initial weight. So it has simpler structure. So you don't have that phase transition. So that phase transition actually comes from the from the reversibility, from the fact that you also take the non-orientation, the fact that you don't. So the way to see it, actually, a nice way to see it is through, for instance, the proof of Angel Crawford and Cosma of recurrence. So you remember your tree of first visits. So because once you have visited once an edge crossed when you arrive at the next step, so you are kind of pushed back to your towards the origin through that tree of first visit. So intuitively, so the orientation matters. So if you are completely oriented, then obviously so you don't have that effect.
But what you're saying is that like in a star edge reinforced walk, you're not completely oriented. Like you're not.
You can be completely oriented. I should have said it in the video. I forgot. You can also you can simply take, for instance, two graphs. So you take one oriented graph, and then you take that copy of that oriented graph, but in the other direction. So instead of having edges ij, you take edges j star I star, right? So you reverse your graph and you make them disconnected,